Hello, my name's Samuel Day. I was part of the engineering club's quadcopter team. I was part of the sensors and soldering and programming of the quadcopter. This is our assembly. We kept the teensy that was given to us and utilized the quick shield, which allows us to quickly put on sensors that we got, such as the infrared. There's a LiDAR. These are attached to a camera, which would allow us to measure distance, and this would allow us to measure infrared and heat data. We had the XP on there that tell us data wirelessly. Oral presentation. We built up our drone assembly quite like the final version, as you see here, and we had ability to quickly detach items and sensors. We hadn't tested any live data collection. We had tested the sensors and tested them on the drone itself, but we hadn't tested it much with flying. We didn't know how the batteries were going to operate. Also, our sensors weren't programmed to read as efficiently as our fly-off data was. It was just test data. The walkthrough gave us a lot of understanding about the course and environment we were going to go through. This is camera footage of our walkthrough. We did fly through it, but we also had some walkthrough data collection. And this is just to help us with photogrammetry. So how we're going to map photogrammetry is creating a 3D model. This is how we're going to map the field, and we're going through the practice of doing that. And we also learned how we want to fly around and what to fly around during each phase. And it really helped us with how our phases were going to operate. This is some more footage, close-ups, and how good of footage we got for certain items and photos. This was the actual fly-off. To get perspective of our environment, these are 4 photos. And this is where we were all stationed in the back here. This is footage from behind. And this captures most of the items in it. You see there's 1, 2, and 3 packages. There is a photo here and a photo on the tower. There's a water bucket and a sand. Some footage to represent what we did or where we were. And more footage from behind. This is one of the photos, and this is a close-up of it. This is also the close-up of the photo on the tower. This is the back, and it's flipped upside down because the actual piece of paper was upside down. And this is how far we could read, and we had glare that injured our ability to see all the way. This is close-ups of the sand and water bucket. And this is a moment where we detected magnetism, and that magnetic bag was the packet located on the ramp. That first packet located next to the sand, it seemed quite cold compared to the rest of the environment, but that could be due to it being on the floor. And then the third packet in the far back, we never actually got any proper data for, but we did land our chemical sensors next to it, so we can say there was no chemical signature next to it. For infrared, we can see sand, and we can notice that it's very cold. Our data always represented the hottest and coldest pixel that it was detecting, and you can see that for 2 seconds it was representing 8.75 degrees Celsius, and on the 8x8 pixel array, you can see when it got dark, it was showing you that it was cold. This is for the water bucket. We can see that the water bucket was cold, and it averaged 9 degrees. We noticed that the packet on the ramp, the one that we detected magnetism on, It seemed a little bit hot, and you can see when it's bright. So it seemed a little bit bright, it seemed a little bit hot, and there's a noticeable little difference in Excel.
Hello, my name is Zachary Herman. I'm a sophomore at Century College, majoring in aerospace engineering. This is the map we generated from the images we collected by counting pixels. All the measurements in the map are accurate within an error of plus or minus 5 inches. We also used the video captured from the drone's camera to create a 3D model using photogrammetry. These are some of the images of the model we created. As you can see, the model is not very good, which is why we decided not to use it for our mapping purposes.
I'm Patrick Miller, and I am Teams Coordinator, and I work with sensors and programming. Ambient pressure was found by the BME 680 to be 986 HPA, with a margin of error of 0.12 HPA. Ambient temperature was measured by two different devices. The BNO 055 found a mean temperature of 23.47 degrees Celsius earlier in the run. The BME 680 later found a mean temperature of 22.57 degrees Celsius. That device has a 0.5 degrees Celsius margin of error. Ambient humidity was found by the BME 680 to be 18.0%, which has a margin of error of plus or minus 3%. The chemical sensors all operate as variable resistors, whose resistance lowers in the presence of substances of interest. The gas sensor on the BME 680 did not find a positive signal for a unusual concentration of volatile organic compounds. It instead displayed a trend towards a baseline value. The hydrogen sensor, the MQ-8, recorded a very spiky signal, but the spikes in the signal corresponded very strongly with periods where the drone's rotors were running, which may have affected the operating temperature of the sensor. The methane sensor, the MQ-4, for some reason experienced some kind of fault or failure during the fly-off, where it did not settle on any recognizable value. Measurements before and after the fly-off found a typical decline towards a baseline value. The ammonia sensor, the MQ-137, recorded a spiky signal as well, but also could be correlated with periods where the drone's rotors were running. Outside of that, no clear signal was found. As a review of the outcomes, the sensors were not found to be highly effective, or at least no clear positive signal was found. Possible improvements in the future may help isolate the sensors from effects from the drone downdraft and possible cases of electrical load exceeding what the drone's circuitry was permitting.